There's a law that quietly governs every model you build. You optimize what you measure. So if you measure the wrong thing, you'll cheerfully optimize the wrong thing. Choosing the right metric isn't a detail, it's the whole direction of the project. Let's see why, by building the numbers ourselves. Picture 100 transactions. 99 are legitimate, and just one is fraud, the needle in the haystack. Now here's a lazy model that always says not fraud, no matter what. Let's actually grade it. It's right on every legitimate transaction. That's 99 correct out of 100. Watch the accuracy climb to 99%. It looks brilliant. But now look at the one fraud. The model missed it. Frauds caught, 0 out of 1. The single thing we cared about, and it caught none of them. Accuracy hit a completely useless model. The reason accuracy misled us is that not all mistakes cost the same. There are two very different kinds. A false positive, crying wolf, flagging something that was actually fine. Watch a legitimate case get wrongly flagged. And a false negative, a miss, letting a real case slip right through. Watch a true case sale passed unnoticed. Which of these hurts more depends entirely on your problem. Compare two systems. First, a spam filter. The painful error here is a false positive, an important real email banished to the junk folder, where you'll never see it. So we favor precision. When it flags spam, it had better be right. Now a cancer screening test. Here the painful error is a false negative, telling a sick patient they're fine, and sending them home. So we favor recall. Catch every real case, even if it means a few extra false alarms. Same underlying math, opposite priorities. The metric has to match the real-world cost. When both errors matter and you want a single number, there's the F1 score. It combines precision and recall with this formula, 2 times P times R, divided by P plus R. Watch what it does. On the left, a model that aced precision at 0.9, but neglected recall at 0.2. Plug them in, and F1 comes out at just 0.33, low. You can't fool it by winning only one side. On the right, a balanced model, precision 0.85, recall 0.82. Now F1 climbs to 0.83. F1 only rises when both are high. That's what makes it the honest single score for imbalanced problems. Regression faces the same choice. Here's a model's predictions against the truth, with the error drawn as a red line for each point. Most are small, but one is a big miss. Mean absolute error just averages the sizes of those errors. Add them up, divide by 7, and we get 0.71. Every mistake counts in proportion to its size, fair and simple. Root mean squared error squares each error first. Watch that one big miss. 3 squared becomes 9. It dwarfs all the others combined. After averaging and taking the square root, RMSE comes out at 1.18, noticeably higher. So if one large error is a disaster, use RMSE. It punishes big misses. If every error is equally bad, mean absolute error is the honest choice. Here's the crucial habit. Choose your metric before you tune anything. Because everything downstream, grid search, cross-validation, all of it, will relentlessly optimize whatever number you point it at. Point it at the wrong number, and it will faithfully make the wrong thing better. Pick the metric that reflects real-world cost first, and the whole pipeline pulls in the right direction. So, accuracy can lie on imbalanced data, precision guards against false alarms, recall guards against misses. F1 balances the two. And for regression, RMSE punishes big misses while mean absolute error treats them evenly. Match the metric to what actually costs you in the real world, and choose it first. Once you have the right score, it pays to look closely at what the model gets wrong. Error analysis is next.